In this video, we're going to extend our knowledge of equivalent circuits to the most general case. And last time we asked, what does the source see? And we figured out what we mean by sources seeing things. But in this video, we're going to talk about what the circuit elements see. This is going to open the door to the generalization of what we've already talked about, namely the Thevenin and the Meyer-Norton equivalent circuits. These are very important to understand and appreciate the knowledge they give us. So let's talk about a little bit of an extension of what we've already talked about. If you recall, this was our original circuit. We had a source, and our system was a series resistance, and we know that for that case, V out was R2 over R1 plus R2 times Vn. We used voltage divider to find it. Well, if you're going to actually use that voltage for something, it has to be attached to the sink. Remember our old system thinking that we have to send our message to the sink. And the input to most circuits that we care about look like a simple resistor. And so the question is, if I attach my circuit to the receiving circuit, which is going to look like a resistor, does that change the output voltage V out? You may say, well, the voltage V out is across both the RL and across our original R2, but in reality, it's really across the parallel combination. Well, that changes the resistance, so you should expect there might be at least the possibility of some change in V out. So I want to explore that. By the way, RL, this is standard terminology. This L here stands for load, and that's a term that comes from the power industry. Well, how do we think about this? And here's the way I want to do this. I want to try to figure out, what does the load resistor see? What is the circuit that it sees looking back in that way? That's going to be a key for us. So that's what I meant by, what do the circuit elements see? Well, it's not just a simple resistor, of course. There's a voltage source in here, so the series and parallel rules don't quite apply. However, we can use the principle of superposition here to figure this out. If you think about this for a little bit, if I drew a box around here, this just looks like a regular old generic circuit with the current defined going in the positive side of the voltage defined for it. And I could figure out the voltage if you just gave me the current. But because of the presence of the source, there's going to be an additional term, which is the part of V that's due to the source. So the principle of superposition says that voltage V will be equal to the sum of the voltage you get when you set the voltage source that's inside Vn to 0, plus the part you get when you set the input current to 0, and that'll give you the part of V that's due to Vn. Okay, so let's do the first one. When we set the voltage source to 0, that's the same as a short circuit. So remember, a voltage source supplies some voltage for any current. Well, if you set that source to 0, now the voltage is 0 for any current. That's the definition of an ideal wire or a short circuit. So now, what do we see looking into the circuit? We see R1 in parallel with R2, and so we know that at least that component of the output voltage is given by a simple resistive-like term. And now if you go on to setting I to 0, so I'm going to turn the source back on. Our source is alive and well. And then setting I equal to 0 means there's nothing attached to the terminals. And what we have is the same circuit that we had before that we already analyzed. You simply use voltage divider to figure out what V out is, and this is what we got last time. So V is going to be the sum of two terms. If you think about that as a system, and you want to know what the VI relation is, you can use this superposition principle, and we see that, at least for this case, that's what we get. We get that V is equal to some resistance-like term times the current plus a source-like term. Well, that opens the door to a really interesting result. So let's define something. I'm going to call that REQ, equivalent resistance. I'm going to call the second term VEQ, equivalent voltage. And I want to point out that something that of this form, which can be written like that, that is the same VI relationship that applies to this circuit. And of course the subscripts EQ here mean equivalent. So these two circuits you cannot tell them apart just from the terminals. They look identical because their VI relationships are exactly the same. So I can express, in particular, as a very simple circuit, a very complicated circuit containing voltage sources and resistors. We're going to show in a second that you can, in addition to voltage sources, you can have current sources too. So this is called the Thevenin equivalent circuit, and it's named for a late 19th century engineer who developed the equivalent circuit idea while he was learning to teach a course at the École Polytechnique in Paris. So that's quite interesting. But there's even more. So here's our simple little circuit that we've been talking about, and here's the Thevenin equivalent relationship for it. I'm going to turn that equation around. I'm going to write this as I equals something. And I'm going to call that last term IEQ. And I want to point out that set of that equation describes behavior of this circuit, where there is a current source in parallel with REQ. It's the same REQ that we had when we talked about the Thevenin equivalent. There's no difference. This is called the Meyer-Norton equivalent circuit. Meyer-Norton is named for two engineers, Edward Norton, who is from the US, and Hans Ferdinand Meyer, who is from Germany. And they developed this idea at almost exactly the same time, but independently. So we have two different ways of thinking about a circuit. So we think about these terminals, this pair of terminals out here, is a place where you're about to attach something, some other circuit. And you want to know what does that circuit look like in order to simplify your calculations. You can describe it either as a voltage source in series with a resistor, or you can describe it as a current source in parallel with the same resistor, whichever seems to be the easiest approach for your application. They both apply. You can do either one. So this really simplifies things. In fact, this is a profound result. This says that no matter how complicated a circuit is inside, consisting of sources, current sources, voltage sources, and resistors, it all can be summarized as a simple voltage source in series with an equivalent resistance. This equivalent resistance is sometimes called the output resistance. And we'll see that this is an important quantity in just a second. Now, and this equation ties these two equivalent circuits together, so that VEQ is REQ times IEQ. So if you find one, you've got all you need to find the other. No problem. So, one issue with finding equivalent circuits is, can you really do it, find the equivalent voltage, equivalent resistance, without looking inside the box. Can you make measurements just at the terminals to figure out what those quantities are? And the answer is yes. The first thing we do is to find what we call the open circuit voltage. And that means we set this current to 0 and we look at the voltage we get. Well, if you look at this equivalent circuit, if you set that current to 0, that means there's no voltage drop across that resistor. So V is just equal to VEQ. So if you do that for a real circuit, you just open circuit the terminals, don't attach anything, and just measure the voltage. That voltage that you measure is the equivalent, the Thevenin equivalent voltage. Similarly, you can short circuit the current. So what that means is that you short circuit these terminals, you put a short across there. That sets the voltage to 0, of course, and then you measure the current. And when you do that, if you look at this equivalent circuit, that short circuit current is just going to be minus VEQ over REQ, and that's the negative of the Meyer-Norton equivalent current source. So by making measurements at the terminals, the open circuit voltage and the short circuit current, you don't have to look inside the box, as it were, to figure out what the equivalent circuits are. So let's go on to a simple example. And so to show these ideas, I want to find the equivalent circuits for this example circuit, and I could find explicitly the Thevenin equivalent. I could find the Meyer-Norton equivalent. Well, I'm just going to find the equivalent quantities VEQ, REQ, and IEQ. So the first thing we can do is set all the sources to 0. If you set the source to 0 in the Thevenin equivalent as a short circuit, and what you see from the terminals is just that resistor. If you set the current source to 0, that's the same as opening it up. And then again, you also see REQ. So here, if you look inside the box, we see we have a current source. A zero-valued current source is the same as an open circuit. No current flows for any voltage. That's the definition of an open circuit. And what I see when I look this way into there, I see R3 is in parallel with this series combination. So we can use our series and parallel formulas, and we get that for REQ. So that's the source resistance of our circuit. Now, suppose we want to find VEQ. I'm just going to use our terminal-only results. I'm going to open circuit the voltage. So there's nothing across here. This is 0. And now we measure the voltage. Well, this voltage is going to be given by some dependence on this current source. And since it's a current source, it's a whole lot easier to find the current through here. And then I'll multiply that by R3 to get the voltage. Well, because we have this in parallel with this now, from the point of view of the current source, I'm going to use current divider, which is going to be the other resistor divided by the sum of that one plus this series combination. And when you all get said and done, that's what you get. So here's the current divider part, and then I just multiply by R3 to get our voltage. So that is the Thevenin equivalent voltage for this circuit. It's a little more complicated than you might think, but it's pretty easy to find. And then finally, I'm going to find IEQ, which I'm going to do by finding the short circuit current. And I just put a wire across here, and so what that does, by setting this voltage to 0, that shorts out this, so that resistor isn't there. Doesn't matter if it's there or not. And so, again, I'm going to use current divider because I have a current source here. Well, the current I is going to be the negative of that current. And I use current divider, so current divider says that current is R1 divided by the sum of the resistances times IN. And I stick a minus sign in front because of the directionality of the current. And I get this for ISC, the short circuit current, which I know is the negative of IEQ. So we could have divided the equivalent voltage by the equivalent current to find REQ. In finding REQ up here, what we did was look inside the box. And you don't really have to do that, but it's nice to know you have a way of checking your answers. Set the sources to 0 to find REQ, find the open circuit voltage to find the Thevenin equivalent voltage, find the short circuit current to find the Meyer-Norton equivalent current source, and then the ratios should work out to be the other. Everything should check. Okay, so what do we discover? What we discovered is that all circuits consisting of sources and resistors are equivalent to one source, be it a voltage source or a current source that's in series or in parallel with a single resistor. No matter how complicated that circuit is, from the point of view of the connection points, the terminals, it is a very, very simple circuit. So that means that we can use either of these equivalent circuits, the Thevenin or Meyer-Norton form, the voltage source or the current source form, whichever seems to be appropriate, that makes solving the problem easy. What I mean by that is you're now going to attach something to the terminals and determine things. And depending on what you're interested in finding and how complicated the circuit is you attach, you would use one or the other. Now, remember how we got started on this. Remember we were attaching our sink to our original circuit that we've been talking about. And the issue was what's called loading. And loading is a term that means that if I attach the wrong kind of load resistor for the given application, this V out will change. That's called loading down the original circuit. Well, I want to figure out what values of RL will not contribute to loading. What kind of resistor values can the sink have so that the V out doesn't change from what it is if nothing was attached? Well, we now know that our system looks like this, which is, I'm going to use the Thevenin equivalent because I have voltage that's the output, and the voltage I want is across RL. Well, what is V out for this really simple circuit? Well, it's the voltage divider. It's very easy to find. And what values of RL will allow V out to be equal to VEQ? Because when RL is infinity, that's the same as attaching nothing, and that's where we started. So I know that the output that I want is VEQ. Well, I think it's pretty clear that what we want is RL to be big. But big relative to what? And the answer is it has to be big relative to REQ, which is R1 in parallel with R2. So as long as the load is big compared to whatever this parallel resistance turns out to be, then you can attach the sink to the circuit and it won't change V out. However, if RL is smaller than that quantity or comparable to it, that output's going to change. And that may not be what you want. It depends on the application. This little simple example points out the power of using equivalent circuits.